Hi everyone, my name is Marvin Cheng. The topic that I'm going to present today is identification of contact avoidance zones of robotic devices in human-robot collaborative workspace. Uh, this work is done at the National Institute for Occupational Safety and Health facility in Morgantown, West Virginia. Unfortunately, one of our authors, Miss Elena Dominguez, passed away in May. She has a great knowledge on robot safety and has contributed significantly on the NC safety standards for industrial robots. I have started to collaborate with Elena since 2019. I would like to thank her for her contribution to this research before I start my presentation. Also, I apologize that I cannot attend the conference in person due to some issues. This is the outline of my presentation. I will start to talk about the motivation of this research. Then I'm going to explain the experimental setup in our facility. Next, I'm going to talk about obstacle detection and robot localization using specific devices. Then I will explain how to define the contact avoidance zones around human workers. Next, I'm going to discuss the navigation of robot with the consideration of the defined contact avoidance zones, and conclusion will be drawn. So the motivation is recently various industries are increasingly adopt robotic devices for efficiency and productivity gains. Therefore, collaborative workspace where humans and robots work together are becoming commonplace. Ensuring the safety of human workers alongside robots is important. Unfortunately, though some safety means have been suggested in the safety standards, human-robot interaction has not been regulated according to the recent development of collaborative environments. Unexpected physical contacts between the humans and robots in workspace can lead to injuries. Therefore, we define contact avoidance zones, which means human-robot contact does not occur within this zone. These zones apply to robot operations are essential to prevent such contacts. In particular, current safety measures often lack integration and precision. This research aims to bridge the safety gap by integrating contact avoidance zones, indoor localization, and obstacle detection for safe human-robot interact collaboration. In our experiment, we have two types of robots. One is collaborative robots, which is designed to work in close proximity to humans. Another one is mobile robots, which provide flexibility and mobility within our experimental workspace. For the machine vision, we adopt two types of sensors. One is depth camera, which is used to acquire the depth information of the surrounding area for the robotic devices. And the LiDAR is to detect any obstacle that the robot is going to detect while it's moving around. And for the localization, we were using Bluetooth beacons and receivers to determine where the robot is located in the experimental area. We also use RGB camera to scan the existing QR code in the area to determine its absolute position. On this page, we're talking about some of the operation of our robots. So for the sensors, we have three types. One is RGB camera, depth camera, as well as Bluetooth receiver. Those are the sensor we use for the robotic devices. So when the robot is initialized, it will return to its specific location. Once it starts to operate, it will start to detect the human motion in the surrounding area using the depth camera. And this information is going to be used for synthesize the contact avoidance zones. Another module is localization. So the robot will also start to collect the Bluetooth signal from the surrounding area to determine where it is being located. So it will be able to decide which path is going to move through or have the main factor to move. Once we have those information, then the path is going to be planned accordingly. One thing I didn't mention in the previous slide is that how do we generate the map? So the map is not acquired in real time. We have been acquired the point clouds for the experimental environment. So in order to acquire the two-dimensional map or the three-dimensional map, we are not going to use the point cloud because it's too complicated or too busy for the robotic controller. So instead of using the point clouds, we divide the space into 75 by 70 by 25 cells based on the width, length, and height. And if we see any point clouds is fall within individual cells, the cell is going to be marked as occupied, which means the robot is not going to get into this specific region and do some operation. And so you can see the second map over here, which is a 3D map, but it's converted from the previous map. And we can use LiDAR to update this map on the fly. For the indoor localization, we use multiple Bluetooth beacons located in the workspace. And before we start to determine the position of the robot, we will need to know the strength profile of individual Bluetooth beacons. Once we have those strength profiles, we can use the receiver to receive the individual signal from the beacons. Once we know the strength of the individual beacons, then we can start to determine what is the location based on the geometry relationship, as we can see over here. And as I said in the earlier slides, we also use a QR code that can be detected by the RGB camera, and those QR code is serving as the calibration landmarks for the robotic device. Then once we get those information, the next thing we need to do is to define our contact avoidance zones. Contact avoidance zones are typically defined using sensors, such as cameras or distance sensors, that detect the presence of humans in the robot vicinity. The zones also define the regions around the human worker or the surrounding obstacles, where the robot should not enter or should not operate to prevent any potential physical injury. So this is the definition of contact avoidance zones, but how do we apply that to the real human worker or on the obstacle? So we can use the information of configuration space of individual joints. If we can identify those configuration space, then we should be able to mark those space as contact avoidance zones. However, it can be very difficult because depth camera can acquire more than 30 joints for a human body. So if we attach the contact avoidance zones for all joints, it can be very busy and very time consuming. So instead of using this method, we attach a simplified region to the human body. So as you can see in the second figure over here, when we attach the configuration, the contact avoidance zones, individual size is 0.3 meters away from the closest point of the human body. So with this set, we should be able to mark a specific region around the human worker. And this is over here, this is a real-time generation of the contact avoidance zones for the human worker. However, I would need to say this method is applicable for static human worker, which means he is not going to move anywhere. For moving worker, then we would assume it's going to be 1.6 meters per second, and the fresh rate is set to be 1.5 seconds. So with that said, we should be able to know the contact avoidance zones, which has a radius or the distance 2.4 meters away from the boundary. So when we have those information, we should be able to define the contact avoidance zones for the human workers while it's moving in the workspace. With all those information being defined, the next thing we need to do is to do the path planning for our robotic device. For the first example that I'm going to demonstrate is the how do we plan the moving trajectory of the end effector for a collaborative robot. So in this case, we're going to move the end effector from its initial position to the shelf and pick up something, then drop it to the conveyor. And as you can see over here, the conveyor and the shelf over here should be marked as occupied when we define the movable region. With that said, the workspace has been gridded into limited amount of cells, and those area has been marked as occupied. So when we start to do the path planning, we use MATLAB and Python to implement the path planning algorithm. And the algorithm we use is A* algorithm in 3D space, which is something we developed in our lab. So when we use this specific algorithm, from the start point to the pickup location, it takes about 6 waypoints. From the pickup points to the drop-off points, it takes another 12 waypoints. If we have something happen in between, then the A* can recalculate within 1 second, which is pretty efficient for this configuration. Another thing we need to do is for the mobile robots. For the mobile robots, the robot is specified to move from a start point to an end point, but because the human worker can be moving around in the workspace, so it needs to have several waypoints to detect whether a human worker is present in the workspace or not. In this case, we set before it reached to its end position, we set an waypoints over here to verify whether the moving trajectory needs to be updated or not. In the second scenario over here, if the robot detects the presence of a human worker, then it will start to move around the human worker and still achieve its end destination. However, if it found it's not passable, then it will start to generate another path from the waypoint to the destination using a longer route. So with this kind of approach, the robot should be able to avoid the human workers activity, which also ensure a safe work environment. Conclusion. In this study, we have used depth camera and LiDAR to generate the spatial mapping as well as the planar mapping for the robotic devices to use. And we also use Bluetooth localization technology to determine the position of the robot in the experimental area. And we also use the depth camera to identify and determine the contact avoidance zones surrounding the human worker. So combine all those things, we provide some kind of method to do the path planning for both the end effector of collaborative robot as well as the mobile robots. In the future, we would like to update our dynamic path planning for more efficiency, and we should be able to better define the contact avoidance zones based on the human-robot interaction research we're recently doing right now. That's my presentation today. Thank you very much for your attention. If you have any question about this study, you are more than welcome to call me or drop me an email. I will be glad to answer the questions. Thank you very much.